So thank you everyone for coming. It's my pleasure to introduce Aidan Friederich and his dissertation defense. Aidan came to us about 5 years ago as a fresh-faced new grad. He's still, we haven't beat that out of him. He looks exactly the same. From Colorado with a dual degree in mechanical and biomedical engineering. I'll just say Aidan's been a tireless worker in the lab. He's a doer. And today we will find out whether he's learned to become a thinker. So the way this will work is Aidan will give his presentation. He'll take questions for clarification only. All right. Then after he's finished, the floor will be open for any kinds of questions. So you can probe, you can ask the questions he planted with you last night. And then we'll dismiss everyone except the people on Aidan's committee. So Dr. Hadid, Dr. Del Torio, Dr. Musa, Dr. Gustafson, and myself. Then after Aidan sweats a little while from our private session, we'll invite everybody back so you can hear the results. All right?
Perfect.
Go
Thank
ahead.
you so much for that introduction. First, I want to thank everybody for being here. I really appreciate you taking the time on the coldest Friday. I think I could have scheduled this on. And I especially want to thank my committee for all being there for me. So today I'll be discussing my dissertation, which is entitled Expanding Seated Posture for Individuals with Trunk Paralysis through Feedback Control of Peripheral Nerve Stimulation. As I am targeting individuals with trunk paralysis, the most common form of reason for this is a spinal cord injury, which affects roughly 300,000 people in the US. This represents a breakdown of communication between the central nervous system and the periphery, and results in a unique prognosis depending on the level and severity of the injury. For example, thoracic injuries can cause trunk paralysis and paralysis of the legs, and cervical injuries, on the other hand, could also cause paralysis of the arms. A spinal cord injury has an impact on an individual's quality of life, but it has been shown that individuals with higher levels of independence or functional ability have a higher quality of life. Thus, one potential avenue to improving these people's lives is through improving their functional abilities. Our lab, in order to improve function, our lab has leveraged an implanted stimulator. This is capable of activating typically paralyzed muscles and causing them to contract. Current is applied to electrodes placed near peripheral nerves, and then those nerves are then connected to muscles, and once the nerve activates, the muscle then contracts as a result. Timing these contractions with control systems has helped individuals with SCI to stand again, step, as well as biking, and etc. The application I will be talking about is applying this stimulation to seated stability. Seated stability has been consistently rated as a top priority for recovery for individuals with SCI, and this is partially due because it's an important part of the kinematic chain in reaching actions. Individuals with able-bodied trunks even employ those trunks in order to reach objects even within arm's length. It's part of that motion. And then individuals with spinal cord injury often have to lean away from the object in order to counterbalance the weight of their targeted object, or have to use compensatory strategies such as a hand on a wheelchair in order to have that stability during reaching. It also is a reason for decreased trunk strength is a common reason for falls in this population as well. The main movers of the trunk or the muscle groups that we will be targeting are the erector spinae. This causes extension and lateral flexion of the spine and runs the entire length of the back. We are targeting the section at L1 and L2 of the vertebrae. the quadratus lumborum, which also causes extension and lateral flexion of the spine, the iliopsoas, which causes flexion and lumbar flexion of the hip and lumbar spine. And then the hips, we're targeting the posterior section of the adductor magnus, and this causes thigh adduction and hip extension. The glute max, which extends and externally rotates the hip. The glute med, which causes hip abduction. And a section of the hamstring, which causes hip extension. While these are the targeted muscle groups, it is important to note that current can spill over to adjacent neurons that recruit different muscle groups. And we are often only recruiting a subset of these muscles. Therefore, it's very important to consider the functional outcomes as a result of stimulation and not assume function based on the targeted muscle group. Back to trunk stability, activating these muscles with a constant level of stimulation allows the user to maintain upright posture. As you can see in this example, when this individual turns the system on, she's able to assume an upright posture without slouching. This constant level of stimulation has been shown in the past to increase reaching distances and improve posture. However, it is unable to compensate for perturbations by changing that level of stimulation, and it cannot assume different leaning postures. That brings us to our overall research objectives of this dissertation. The first one is to develop and implement neuromuscular stimulation controllers to maintain and expand seated postures to enable functional tasks. The key points of this objective is both maintenance of those postures. We want to maintain whatever posture they are in, and also facilitate that expanded range of postures, such as leaning, for example. And this all needs to be done while enabling activities of daily living. The second main objective is to develop a clinical implementation strategy to translate seated posture controllers into the home. Any innovations in the lab need to be translated into everyday use of the people with SEI, and therefore the second objective, we tackle some challenges that could hamper clinical deployment. To achieve the first objective, we tested the following hypothesis. An upright feedback controller will reduce postural sway during seated functional reaching tasks and will quicken return to erect movements compared to no stimulation or applying low levels of constant stimulation. This hypothesis is intended to test both the ability of the controller to maintain that seated posture by reducing the overall postural sway of the individual and its effect on a functional task, attacking those two components of that research objective. Testing the hypothesis brings us into the aims. Aim 1 relates to enabling upright and leaning postures in individuals with trunk paralysis. And then aim 1.1 is detailing that evaluation of the controller performance during a functional seating task. Then aim 1.2 and aim 1.3 relate to that expansion of leaning postures. I'll discuss those later on. And then aim 2 addresses that second objective of clinical implementation. And that will also be discussed later on. The upright controller that we will be examining in this first hypothesis infers position of the trunk from an accelerometer that we place on the chest of the individual, and then one PID controller regulates stimulation parameters sent to muscle groups that cause extension movements of the trunk, which is forward and backwards, and another PID controller regulates stimulation parameters that causes lateral movements of the trunk. The controller will be active while the individual moves a weighted jar to different stations on a table. Here's an example of how the system works. For example, if the trunk flexes forward, we would want to activate those two erector spinae muscles in the back in order to extend the trunk back to arrest that forward movement. If, for example, the individual leans to the right, we would activate left-sided muscles such as the left quadratus lumborum or the left erector spinae in order to correct that movement and maintain that upright seated posture. Here is the system in action. On the left is no stimulation, and you can see that she struggled more with the task, is relying more on compensatory strategies such as pressing on the abdomen and using her arm to return upright after returning the jar to different positions. And then on the right, you can see that she appears more confident. She's able to move that jar around quicker, and that the stimulation is aiding in that returning upright motion of that individual. The first component of that hypothesis was a reduction in postural sway during these seated functional tasks. In order to assess this, we plotted the pitch angle of the individual, which is movements in extension, forward and backwards, and then plotted that against roll angle, which is movements laterally. Then we fit an ellipse to this, and the area of that ellipse relates to postural sway and characterizes the postural sway of that individual during the reaches. We did this test with 5 individuals with spinal cord injury, and a reduction in postural sway was significantly reduced in 2 of those individuals during the reaching tasks. This partially supports our hypothesis. The other aspect of the hypothesis was that a controller would aid in return to upright motions after the trunk is deployed to accomplish the task. Reducing this value reduces the amount of time that individual is potentially in an unstable posture. To examine this, we plotted the pitch of the individual during the trial for both deploying the jar to a target location and returning the jar back to that home location. And then we took the time difference between the peak of that movement and when they returned back to that upright posture. The controller significantly reduced the time upright in 4 of the individuals, as observed here, compared to no stimulation. And but this was only for deploying the jar to a target location, and this significance did not continue when they were returning the jar back to that original home posture, except for that 4th subject, as you can see in this graph. Again, this partially confirms our hypothesis for 4 of those individuals, at least when they are deploying the object to a target location. Overall, our hypothesis was partially confirmed for postural sway and return to upright movements. In the 4 individuals who saw a quickened return to upright motion, the time away from a stable upright posture was reduced by 0.17 to 0.32 seconds, which would likely add up, during if this individual would use the controller throughout the day on various functional tasks. The partial confirmation of our hypothesis could be due to the unique compensatory strategies the subjects employed. We observed increased hand pressure on the abdomen. Subjects often pushed off the jar to aid in returning to upright, and sometimes use their arm to help in that return to upright motion. There are methods of reducing these compensatory strategies in the lab, but considering these controllers, they're intended to be used in the home where compensatory strategies will be used regardless. It's better to design controllers with these compensatory strategies in mind, and then potentially even test the controller effect on them over time. That moves us to the second component of that main research objective, which is to expand seated postures. The hypothesis we tested to achieve this goal is that a leaning feedback controller will enable perturbation-resistant leaning postures that are perceived as stable while expanding available workspace compared to no stimulation and constant stimulation. This hypothesis reflects the requirement of leaning postures to remain stable, even if the individual is perturbed. They need to expand the individual's workspace because otherwise there would be no reason to move beyond that upright posture. And finally, the user needs to feel stable while using them, or they would not be used in the home. Expansion to leaning postures requires a greater consideration of the muscle forces and moments. Muscles act across multiple degrees of freedom, and in order to achieve this leaning posture shown in the simulation on the right, in this case, red, a higher level of red demonstrates a higher level of activation in that muscle group, and then blue indicates lower level of optimization. If example, I increase the activation of the right erector spinae to this balanced set of muscles, the leaning posture is unable to be maintained. So we need a method of characterizing the muscle forces and moments so that we can determine the correct muscle activations to achieve these leaning postures as shown in this simulation. This gives rise to AIM 1.2 and 1.3. AIM 1.2 refers to the identification of trunk and hip muscle contractile properties through a system identification approach. And then AIM 1.3 leverages those findings from AIM 1.2 in order to maintain static leaning postures by combining subject-specific muscle properties with feedback control. To characterize the system forces and moments, we designed the trunk and moment transducer. This device holds an individual underneath the armpits, and then forces that are applied to the trunk by the stimulation are then passed through the device into a load cell at the back of the device. You can see when we apply a stimulation to the system, the muscles contract as a result, and a moment can be measured on that load cell as a result of that stimulation. One aspect we wanted to model was the muscle recruitment in response to stimulation. Muscle recruitment typically follows this pattern when activated via stimulation. There is a dead zone region where increasing levels of charge doesn't result in increasing levels of force for the muscle. And then when you can reach this high slope region where increases in stimulation result in direct increases in force, and then the muscle saturates and it's unable to produce more force even despite increasing levels of charge injection. Previously, we have been approximating this curve with a linear fit between the end of the dead zone region and the maximum stimulation value that we have available. But this means that we are not accurately accounting for this region of the graph, potentially introducing errors. To determine muscle recruitment, we ramp stimulation from 0 all the way up to the maximum value and measured the forces and moments produced by that individual. You can see this muscle displays a very similar characteristic of that was shown on the previous graph. There is a dead zone region where that stimulation does not result in increases in muscle force. Then there's this high slope region between 100 and 150 pulse width, where that changes in stimulation result in a direct muscle change in the muscle force produced. And then the muscle saturates, as you can see here at the end. We fit these recruitment curves to a sigmoid curve, and this was done with 4 subjects across 44 muscle groups. And overall, we had an R-squared value of 0.82 and a root mean squared error of 3.1 newtons. The next component we characterized was the subject-specific moments that are required to hold leaning posture. A shallow posture, such as the one on the left, requires less support from the muscles to hold compared to a greater leaning posture on the right, which requires more activation from the muscles in order to hold. We need to characterize this such that we know how much support the muscles need to provide in various leaning postures. Additionally, muscles show a force-length relationship. As postures change, the muscle length changes, and therefore force that they produce changes. We characterize this by measuring the moments produced via the stimulation, in various leaning postures. These are the required supporting moments at postures leaning from -30 to 30 degrees. This just involved placing or having an individual sit in the device and then moving the device to different leaning postures and collecting how much support that they need at those postures. These were fit to a plane, as you can see here. These are the moments produced by a muscle while at those same postures, and these postures range from -30 degrees roll to 30 degrees roll, and then 0 to 30 degrees pitch. These were modeled with a 2-degree polynomial. This is for the left quadratus lumborum, and it exhibits a saddle-shaped curve where the optimum force production occurs while the individual is leaning at 10 degrees to the right. This also allows us to determine the directional components of the muscle. And because at any posture, I can determine the extension and the lateral moment bending forces of the muscle. Now returning back to the main goal of enabling leaning postures, with these characterizations, we can determine the correct muscle activations in order to hold this leaning posture. However, with 9 to 16 different stimulation channels, this can be a computationally expensive equation to solve. And in order to control in real time, we need to solve this at least 40 times a second. In order to reduce the dimensionality of the system and thus simplifying it, we leveraged muscle synergies. If, for example, you have two muscles that are providing very similar motions to the right laterally in this case, and on the right side of the screen, and then a muscle on the left side of the screen that is causing extension forces and left lateral movements, you can group those muscles that provide similar actions into a synergy. And therefore, we've reduced the dimensionality of the system from 3 muscles to 2 synergies. And then when we apply the same technique to our 9 to 16 stimulation channels, we can reduce that to 4 synergies, thus simplifying that computation. These synergies have been shown before to be applicable to control of neuromuscular systems, both being able to recreate walking in musculoskeletal models, as well as control reaching, arm reaching in musculoskeletal models and in individual able-bodied individuals. With the characterizations of the produced muscle moments from a couple slides ago, we can identify the subject-specific synergies. The center plot here shows the strength and direction of these synergies. So for a greater projection on the pitch moment results in an increased extension moment, and then roll moments are to the right or left. Synergy 2, for example, recruits a surface left erector spinae channel and a surface left quadratus lumborum channel, and this resulted in a more left lateral bending moment along with some extension forces. Synergy 4, on the other hand, in purple, recruited implanted muscles such as the left erector spinae and left quadratus lumborum, and this also resulted in some lateral bending moments, but predominantly it resulted in extension moments. And then synergy 1 and synergy 3 kind of reflect those of 4 and 2. With these synergies in hand, we can design a controller to leverage them. Again, we will be inferring trunk position from an accelerometer. This time we're placing it on the back of the individual. Then once that individual assumes a leaning posture, that will be considered the set point or that target leaning posture. Those postures are then sent to a feed-forward desired moments, which determines the required support or those moments that these muscles need to provide in order to hold a leaning posture. Those are then added to the feedback control component, which is again comprised of 2 PID controllers, one that controls pitch and one that controls roll of the individual. Those are added together, and then we can use those same synergy calculations to determine the required activations of these muscle groups. Those activations are then converted to stimulation parameters with the recruitment curves that we measured earlier, and then applied to the neuroprosthesis, which inspires trunk movements, which is then registered again by that accelerometer, and the loop continues over and over again. Now that we have a controller, we can test the hypothesis that a leaning posture controller will enable perturbation-resistant leaning postures that are perceived as stable while expanding available workspace compared to no stimulation and constant stimulation. The outcome measures that we are examining for this hypothesis are maximum reach of the individual, perturbation resistance, and perceived stability. Here is an example of an individual attempting to lean without the controller active. You can see as soon as she leaves that stable upright posture, she's unable to maintain a leaning posture beyond that. On the right is the controller in action. There's that initial activation, and then it's able to maintain that leaning posture that previously was unobtainable. You can tell she shakes her head a little bit because she's kind of in surprise that she can hold these leaning postures even after 10 years of being able to undo them before. And she's able to fully explore that space while that leaning posture is being maintained with the controller. She's able to reach fully forward and to the side, and the posture is maintained. Here is another example of a subject reaching forward and down once the controller is able. The controller during these reaches is still able to maintain that seated posture. We tested this with 3 subjects and were able to achieve leaning postures of around 30 degrees with all of them. Part of the main hypothesis is the ability of the controller to expand available workspace. We measured reaching distances while the individuals were upright with constant stimulation and with no stimulation, and then while the individuals were leaning forward. Reaching distances were statistically increased for all 3 individuals compared to no stimulation by 10, 47, and 16 centimeters compared to that no stimulation. It was also statistically increased over that constant stimulation value for 2 of those subjects. This demonstrates an expanded reachable area for these individuals, and the leaning controller thus adding support to our hypothesis. Another aspect of the hypothesis is that the leaning controller will enable perturbation-resistant leaning postures. So here on the right, we can see we had individuals in a leaning posture, and then we applied perturbations to the back of the individual in order to inspire a forward trunk movement. In this top graph are the forces that were recorded from that perturbation. Right below that is the pitch angle of the individual during the movements. And then below that are the stimulation parameters being determined by the controller in response to the perturbation. You can see as a perturbation is applied, there is a resultant movement of the trunk forward in pitch, and then the controller acts by increasing stimulation channels to cause extension and therefore arresting that forward flexion. Subjects were able to resist perturbations of 33, 92, and 76 newtons, thus supporting this portion of the hypothesis that leaning postures are resistant to perturbations up to these levels. The last component of the hypothesis is that leaning postures are perceived to be stable. To test this, we asked the subject after each reach, what was their perceived stability level, ranging from very unstable to very stable. Individuals overall rated those leaning postures during reach as moderately stable to very stable. This was an improvement over the no stimulation case and was on par with constant stimulation. In conclusion, we tested this hypothesis and were able to confirm that leaning postures were resistant to perturbations, perceived as stable, and expanded the individual's workspace. That brings us to the end of our first research objective, to develop and implement neuromuscular stimulation controllers to maintain and expand seated postures to enable functional tasks. We implemented both an upright controller that demonstrated maintenance of seated postures, and then also a leaning controller that expanded those seated postures and tested them with functional tasks. Our second objective is to develop a clinical implementation strategy to translate seated posture controllers into the home. This will be accomplished through aim 2, which is to create a reliable and accurate measure of trunk posture from a group of sensors with unknown orientations. This aim is driven by a next generation of implanted systems. The networked neuroprosthesis has the same capabilities of those previous neuroprosthesis that I've shown, with a major advantage. The NMP is composed of a network of modules that are placed throughout the trunk, in this case, in order to provide different functions. Each of these modules contains an accelerometer, and this is the same sensor that we've been using previously in order to infer position of trunk, but with the advantage of them being implanted. The implanted accelerometer allows an individual with the NMP to just enable the trunk feedback controller at home so that they can use it to accomplish any activity of daily living. However, the signals from an accelerometer are determined by their coordinate frame, or based on that coordinate frame. And we have previously been aligning this coordinate frame with the coordinate frame of the body in order to get relevant information about movement of the trunk. However, the modules in the NMP, because they are implanted, their position needs to, and orientation needs to be determined surgically by the surgeon based on their needs for the module. Thus, we need a way to, we don't know to determine this orientation without prior knowledge of the orientation of the modules. Think of it kind of like a puzzle. Each module tells us something about the body. However, they are incorrectly rotated such that we can't really figure out the whole picture. If we first rotate them, this starts to make more sense. And then finally, if we fuse all of that information from all of the sensors together, you get a whole picture of a complete picture of the whole. In practice, it looks like this. Here we have a participant on the right that is leaning forward and then returning upright. Accelerometers are attached to her chest, but they are placed in orientations that we don't have knowledge of. Due to this misalignment, each of the signals from the accelerometer are displaying different values. Some show large changes in the x-axis during that movement. Others show large changes in multiple axes during this movement. And currently, this is unsuitable for a feedback signal. If first we rotate the accelerometers, be in line with the axes of the body via this rotation matrix, the signals all begin to look similar. Changes occur in the X and Z axes. If we then convert this to pitch and roll with these equations, now the accelerometers are showing that forward pitch motion that individual performed, but we don't really know which one of these is most correct compared to that ground truth. So in order to determine that, we have an additional step. So on the left in that graph, you can see the colored traces are the pitch and roll from those 4 accelerometers. And then that black line is what we are targeting. That is what we're considering for the gold standard. And that is determined from motion capture of the individual's trunk. If we fuse them with the 2 following equations, we can get one measure of that pitch and roll that could be suitable for control. To determine the correct constants for the previous equations that we've shown, we tested this with 6 individuals and performed a calibration procedure. For each of those individuals, we attached an accelerometer, 6 accelerometers, 2 on the chest, and then 4 in the abdomen region. And these were in position or orientations that we didn't have prior knowledge of, random orientations. We had the subject perform motions in extension, and right and left lateral bending, and flexion. This was repeated 10 times with each individual, and 5 of those were relegated for training, and then 5 was later to test our algorithm. Here's an example of a trial. On the left are the raw signals from all 6 accelerometers. The middle graph are after they were rotated and converted to pitch and roll. We want these signals again to be as close to that black line as possible. The final graph is them after being fused together and have one signal of pitch and roll. Overall, this sensor fusion process resulted in R values between 0.95 and 0.99 and root mean squared values between 2 and 5 degrees. This is on par with literature that also is determining biomechanic movements from inertial measurement units. To check if the sensor fusion was compatible with seated posture controllers, we substituted the sensor fusion signal as a feedback signal in a leaning controller and then implemented it with the leaning controller. This top left graph shows those raw signals from the accelerometer. Below is after being rotated in line with the coordinates of the axis of the body. And then right is the fused pitch and roll of the individual during that leaning posture. This individual is assuming a leaning posture of 25 degrees in pitch and 10 degrees in roll, and the controller is able to maintain that posture for over 200 seconds in this case by applying these stimulation values to the neuroprosthesis, thus supporting the fact that this can be used as a feedback signal. That returns us to the research objective again, which is to develop a clinical implementation strategy to translate seated posture controllers into the home. For this objective, we tackled a hurdle to clinical implementation by devising a way to fuse signals from sensors without prior knowledge of their orientation. The resulting signal is capable of feedback control for our controllers for future implementation with the NMP. I really have 3 main takeaways for you all today. First, that feedback control of upright postures can aid in performance of functional tasks. This is predominantly through a quickening of that return to upright motion after the task. Second, leaning seated postures can be achieved with a synergy-based feedback controller. And importantly, this was built from a system identification of the trunk and hip muscle properties that would also enable future controller development. Those seated postures are resistant to external perturbations and expand the individual's reaching space. Third, a translation into the home was enabled by a robust fusion of distributed sensors without prior knowledge of their orientation into a feedback signal that is suitable for control. Future work should explore new controller designs to enable trajectory tracking. Currently, we only held leaning postures. It would be very useful if, for example, a forward motion of the trunk could be inspired, and then after that individual is done at that leaning posture, return back to that upright position. And this could be accomplished through use of nonlinear controllers. A major focus, however, should be on that translation into the home. To accomplish this goal, we need to further analyze the leaning controller during activities of daily living, and then we need full implementation with the NMP, followed by a take-home study of the controller effects. And finally, I want to emphasize the versatility of the trunk. I've shown how to successfully transfer FNS controllers to the trunk system. I postulate that controllers can also be designed within the trunk system and translated out to control of, for example, the arms or the legs. And development within the trunk system has a lot of major advantages. For One, the controllers are able to be tested at any stage of development. There are accurate musculoskeletal models for initial designs, and then upright seated postures provide a relatively stable posture that allow testing of that feedback only component, such as was done in that first AIM. And then progressive design of high degree of system controllers can begin with just testing 1 degree of freedom, forward flexion and extension of the trunk. And then those can be expanded to 2 degrees of freedom, such as lateral roll, and then even into 3 degrees of freedom by including twisting of the trunk. Muscles are strong enough to resist gravity, which enables trajectory tracking within the leaning space. And these muscles are also easily accessible via surface stimulation if an implant is unavailable. The controllers that are designed have direct clinical relevance to individuals with spinal cord injury. And then I believe that greater adoption of this model could accelerate innovations in this field and help individuals with spinal cord injury. So if you're considering designing a controller, consider designing it with the trunk. First, I want to acknowledge all of the subjects that I've worked with. I've worked with the same people over the course of the 4.5 years here, and they have always been amazing, and I consider them my friends. I also want to thank my committee members for guiding me, especially Dr. Triolo and Dr. Musa Adu, throughout the whole process. They have been invaluable. And I also want to thank everyone in my lab. I didn't list all of the names here, but you all have been fantastic, and I've enjoyed working with you throughout these years. I also want to thank all of the friends that I made along the way. We had a great time at various events, and I will always treasure those moments and hope to return here and meet up with you all again. Then I want to thank my family who were all able to make it today. This is us with our annual tradition of cutting down a Christmas tree just from the woods. Don't worry, we get a permit, so it's allowed. And this is actually my second PhD defense because my mom defended her PhD when she was pregnant with me. So I think doctor is in order, to be honest. But they've always been so supportive, and I always have the greatest time with you all whenever we hang out. Finally, I want to thank my fiance. She's been my greatest support system since I've been here. And I'm just really glad that I found her. We got engaged recently, actually, at Glacier National Park, which I would highly recommend. The glaciers are going to be gone in 10 years, so time's ticking. And then she's just been great, and I'm so excited to spend the rest of my life with her. Thank you all, and please let me know if you have any questions.
Hi, I'm Dave Smith.
Floor is
I have a
open for
question.
questions from the audience. Also, if you're online, I'll be monitoring the chat. Just type in your questions and Aidan will attempt to answer.
All right. They won't let me.
Yeah, no deal.
Yeah, so
Back
when
down.
you have sort of your metric for returning to upright, right? So
Yeah.
you measure from the peak to the trough, right?
Yes.
My question was
Was always trained to ask a question.
from like a steady state position, because I can imagine like you could have a controller that does overshoot a lot on the return. So why not stick like
I don't know how to ask this.
Yeah, so that was basically arisen out of the need to have a very clear signal that we can objectively determine throughout the entire process, which was applied to, I think, the hundreds of reaches that we performed. So we could we could support the fact that this deploy peak was easily identifiable, and then that return trough was easily identifiable. That function of controllers to overshoot was less of an issue in this case, because when that overshoot occurred, that individual would just hit the back of the backrest. And so you would just kind of stop. Oh, hello. Thanks for coming.
Yeah, and I don't know anything about engineering, but I liked your three takeaways. But I think my takeaway would be that it looks like quality of life, really. And I think that's something that is really admirable in what you're doing. It's not just mechanical, it's about psychology. But I do have a question. In the news right now, there's a lot of social criticism of engineering and ignoring the female sex. So for example, in car accidents, it's shown that women are more severely injured than men often, and there are higher fatalities because everything's tested on men rather than women. And all your pictures were of women, but then at the end, when you showed the whole group of your patients, there were a number of men. So my question is, were there any differences in sex between the?
Yeah, so that last image was of the lab and not of
Oh, the lab.
participants, but overall, individuals with spinal cord injury often skew male, just because often it's like car accidents and things like that. So typically we have to compensate the other direction. I've been very blessed to have an even amount of basically male and female participants. As far as I've seen, I haven't seen any differences between the two. There's likely differences with the amount of force that the muscles can produce and also the amount of support that the individual needs. Usually those are matched up. But it is a very important point. I know, for example, with design of exoskeletons for walking for individuals with paralysis, those have been designed for the male body. The individual women often walk with more lateral movements of their hip, and that's not really compensated for within the exoskeleton, which is just a forward motion. So it's definitely something very important.
Thank you.
Yeah, thank you.
Very good.
Oh, thank you. Great question. Yeah. Yeah, so
Can you repeat the question? I'm not sure if people online.
Oh, sorry, everyone. So that was a question referring to how do we determine kind of that maximum perturbation value for our system, and when do we stop applying those perturbations? So in this instance, this was an exhaustive method of determining those perturbations. These were applied with just by hand by individuals in the lab, and it was attempted to start with low pressure and then increase that level of force as those perturbations were increased until that individual was unable to hold that leaning posture, or the controller was appearing to lose that leaning posture. So a way to characterize this, for exhaustively characterizing it, would be to implement like linear actuators that can pull a specific amount of force at any time in order to fully capture like how much percent of body weight that individual can resist.
So how did you get the numbers?
Oh, the numbers were just the maximum perturbation value. So in this case, it would be, I think this is for the 92, and
Where did you get the force?
oh, the force was gotten from a handheld load cell that we just put a basically pad on the other side of and pushed that individual.
So you measured it, but you didn't control it.
Yeah.
So, yeah,
So,
I only get one. This one better be good.
on your 20th slide, you had a fit for polynomial. So you mentioned you fit it to a 2D polynomial, but quite weird. You've gone past that. But yeah, so you fit it to a 2D polynomial. I was just wondering why you picked specifically.
So a 2D polynomial was, it's previously been demonstrated to capture forces and moments of the arm during reaching activities by putting the arm in a haptic master and then collecting the forces as a result of that stimulation. So I replicated that. I also considered other methods such as a Gaussian process regression. I found that to be I found it to overfit a lot. So if we, for example, were outside of this range, like if that individual is leaning at 40 degrees forward, that overfit caused very inaccurate results. And the 2D polynomial has less of that steep offset directly outside of that captured range. So that's why we went with it.
Anybody else? Ms. Mata, do you have a question?
Thank you so much for coming today.
What do you like most about working?
Hanan is a great cook. Learning a new recipe.
All right. Well, thanks for coming. I'd like to ask that everybody except the members and step out of the room for a few minutes.
Oh, I think we do have a question online from Dave Smith. Control of people to Boston Dynamics type robots. Are people more complex to task? So Boston Dynamics robots, if you haven't seen, are these upright robots that are able to do flips. They can jump around, move boxes around. It's very impressive when they do these videos. The main difference of that system is that the engineers know every component of that device. So they know all the moments that the motors can produce. They know the balance of weight in the system, so they can provide a really good feed forward control in order to get most of the way there. And then that feedback helps out at the end. People, on the other hand, require that more extensive characterization of the muscle forces and moments. And there's often a lot of unpredictability in the system. For example, the device that you see here, that individual is seated in it. And there is some possibility of there being some differences between the characterizations that you observe here and the characterizations of when we're testing in a different seated posture. So the human body is often more variable. Thanks for that question.